Welcome back to the Deep Dive, where we take complex, cutting-edge material and, well, we distill it down to the essential, actionable insights you need.
It's good to be back.
Today, we are strapping in for what is, it's truly an enterprise essential at this point.
Absolutely.
A deep dive into the world of Retrieval-Augmented Generation, or RA. And, critically, how the Spring AI framework is making this complex, vital architecture, incredibly accessible for Java developers.
It really is a topic that has fundamentally changed the conversation around enterprise AI integration. It's the bridge.
The bridge, how so?
Well, for a long time, the promise of large language models felt tantalizingly close, but, ultimately inaccessible for companies dealing with vast amounts of proprietary data.
Or needing that absolute real-time accuracy.
Exactly. RA is the foundational architecture that bridges that exact gap. It connects the generic brilliance of an LLM with the highly specific, secure needs of a modern business.
Absolutely. And for our listener, the learner, you're here to move past the elevator pitch. The mission today is to understand not just what RG is in theory,
Right.
but why it is fundamentally necessary for scaling AI within the modern enterprise, and critically, how Spring AI simplifies the entire implementation process. It turns weeks of integration work into, a few lines of configuration.
In many cases, yes. We've got a fantastic stack of source material here, including a really detailed architectural breakdown of our pipelines, from the naive approach right up to the cutting-edge modular designs.
So this deep dive is going to demystify this entire process.
That's the plan. We'll start by framing the foundational architectural challenge that R addresses. It's all about overcoming the inherent structural limitations of LLM.
Knowledge boundaries and context size.
Precisely. If you want an AI that can answer highly specific questions, say about your company's latest quarterly earnings call transcript or your internal product catalog, RAG is the only sustainable, scalable answer.
Okay, let's unpack this core issue then, because I think understanding the problem is absolutely key to appreciating RE as the solution.
It is.
LLMs like GPT, Claude, or Llama, they're brilliant linguistic masters.
Yeah.
But they have these two massive constraints that they break down immediately when you try to apply them to a real-world business problem.
Right.
The first one being the LLM knowledge constraint, what people often call the knowledge cutoff.
Exactly. This is the simplest one to grasp. Think of a foundational LLM as a student who graduated on a specific day, let's say mid-2023.
Okay.
Their knowledge is static. It's sealed off from anything that happened after their last training date. They can't dynamically learn new information, new policy changes, market events, not without a complete and very expensive retraining cycle.
It's like asking a world-class historian about a critical news event that happened 5 minutes ago.
Perfect analogy.
They just don't know it because it hasn't been written down, processed, and sort of incorporated into their historical canon.
And that has profound consequences for enterprise integration. If a user asks a question about internal HR policy changes from this quarter, or proprietary sales figures released last week,
The LLM literally can't access it.
it can't. It will either state it doesn't know, or worse, it will try to synthesize an answer based on outdated assumptions, which leads directly to a hallucination.
Which is a non-starter for business-critical applications. You can't risk that.
You can't. And just think about the cost of constantly fine-tuning an LLM every time a product manual changes or a new compliance stock is released.
That would be astronomical,
That-
prohibitive.
It would be. But, the second constraint is often even more critical and maybe less intuitive for those outside of AI development.
And that's the context window limit.
That's the one. The physical architectural limit on how much information measured in tokens the model can process in its working memory in a single interaction.
Right. And even with all the recent advancements, this is still a hard limit.
It is. Our sources highlight that while models are pushing the downs, we're seeing the new generation hitting 100,000, maybe 128,000 tokens.
Which sounds like a lot.
It does, but that still only translates to roughly, 70 to 150 pages of pure text? Now, think about a global enterprise with millions of proprietary documents, policy manuals, technical specs.
You just can't copy and paste an entire library into the prompt every time a user asks one question. It's impossible.
Ethically, financially, physically impossible. And beyond that, there's a severe efficiency problem. Even if you could cram 100 pages into the prompt, the LLM struggles. It has trouble finding the single relevant nugget of information.
It's the lost in the middle problem.
Precisely. The LLM has to spend immense computational power just processing irrelevant noise. So if the LLM is architecturally static in terms of knowledge and structurally limited in its working memory,
Then RA steps in as the elegant paradigm shift.
this is the solution.
So now that we understand the architectural necessity, let's define RA.
Okay. RAG is an architectural pattern that combines two distinct asynchronous processes. The first is retrieval.
Finding the relevant data.
Right, the ability to swiftly find the single most relevant piece of data from your proprietary, external, or up-to-date sources. And the second part is generation.
Using the LLM to formulate the answer.
Yes, but using it to formulate a coherent, human-readable answer based entirely on that retrieved data.
So you're turning the LLM into a highly effective, contextually aware research assistant.
That's a great way to put it.
Instead of relying on its memory, it basically says, I don't know this offhand, but I know exactly where to look in the documents you just gave me to construct an authoritative response.
That is the core definition. RAG allows LLMs to augment their pre-trained general knowledge with dynamic, highly specific external data sources. The final response is relevant, current, and grounded, in fact.
Okay, so let's revisit that contrast you mentioned earlier. We know RAG is the enterprise standard, but why did it so completely supersede fine-tuning for these kinds of internal knowledge applications?
It really comes down to agility and maintenance. Fine-tuning means you take a pre-trained model and you continue training it on your proprietary data set. You're actually modifying its internal weights, its knowledge structure.
Which is computationally expensive. It needs specialized GPUs. Takes days or weeks.
And it's a nightmare to version control. Plus, if the underlying model update, say, GPT-4 gets superseded by GPT-5.
You have to restart the entire fine-tuning process from scratch on the new model.
Exactly. The maintenance overhead is massive. The RAG advantage, by contrast, is its decoupling. The foundational LLM remains untouched, generic.
So when your internal documentation changes, a new policy PDF is added.
You don't retrain anything. You just run a rapid indexing job to update the vector database. It's a lower computational cost, much faster data updates, and it's infinitely scalable in terms of data volume.
We're talking minutes versus weeks, dollars versus millions.
That's the bottom line. RAG enables these highly accurate, contextually relevant responses without the expensive, slow, constant retraining cycles. That agility is why it's the enterprise standard.
Okay, let's get into the mechanics of them.
To really appreciate how Spring AI simplifies RAG, we first need to commit to memory the foundational naive RAG process model. This is the blueprint.
The blueprint.
We can break it down into three distinct sequential phases: indexing, retrieval, and generation.
This is where we stop talking about the why and start detailing the technical how. We're looking at the data pipeline itself, that offline ETL extract, transform, load process.
Precisely. Phase one is indexing. This is the prep work. It's usually done asynchronously as a batch job or background service, and it's critical. Low-quality indexing guarantees low-quality answers.
So what's the first concrete step? We've got our raw documents, PDFs, wiki pages, JSON objects. What's first?
The first sub-step is data preparation. We start by cleaning the raw data and converting every source into uniform plain text.
Normalizing the input.
Yes, we have to eliminate embedded objects, images, formatting that would just confuse the downstream processes. There are specialized libraries for this, which, of course, Spring AI abstracts away for you.
Okay, so we have a, say, 500-page plain text document. Now we have to deal with that context window limit we talked about.
Which brings us to the most critical step: splitting or chunking. We segment that text into smaller, digestible pieces, or chunks.
And the size of that chunk is an art and a science.
It is. It needs to be large enough to contain semantic context. You don't want a chunk to be 3 meaningless words, but small enough to ensure multiple relevant chunks can fit inside the LLM's context window later on.
So what are the best practices there? My context window is huge. Should my chunks be huge?
No, absolutely not. Our sources suggest that for standard text retrieval, chunks often land in the 500 to 1500 token range. And crucially, developers use a token text splitter, not just a character or new line splitter.
Why is that important?
A token splitter understands the tokenization limits of the target LLM. It ensures the chunk is correctly sized. And you always implement chunk overlap.
So the end of one chunk is the beginning of the next one.
Right, say a 10% overlap. This prevents splitting a critical phrase or topic right across 2 different pieces of context, which dramatically improves retrieval quality.
So we have dozens of small, context-rich text chunks. Now we move from human language into the mathematical language of vectors.
And that is the embedding and storage phase. We take those text chunks, pass them through an LLM embedding model, a specialized neural network, separate from the chat LLM to generate vector embeddings.
Which are these dense arrays of numbers.
Hundreds or thousands of dimensions long, yeah.
Yeah.
They numerically represent the semantic meaning of the text.
Can you elaborate on semantic meaning? What does that actually mean in this context?
Sure. In a high-dimensional space, the distance between these vectors correlates directly to the similarity of their meaning. So if two documents discuss the impact of inflation on Q4 profits, their vectors will be numerically very close.
Even if they use completely different wording.
Exactly. We then store these vectors, along with the original text chunk they represent, in a vector database. This could be a dedicated system like Pinecone, or more commonly in the Spring ecosystem, an extension like pgvector built right into Postgres.
Okay, that completes phase 1, indexing. We've digitized the meaning of our entire document library. Now phase 2, retrieval, kicks in the instant a user asks a question.
Right. The user types their question, and the first step is identical to indexing. Query vectorization. That question is immediately converted into its own vector embedding using the exact same embedding model. Consistency there is vital.
And now we have a query vector and a database full of document vectors. So the core of retrieval is just finding the closest match.
Which brings us to the similarity search. The system searches the vector database for the top k chunks k being a configurable number like 5 or 10, whose embeddings are most semantically similar to the query vector.
And how does that comparison work? I hear terms like cosine similarity.
Cosine similarity is the industry standard for this. It measures the cosine of the angle between two vectors. It ranges from 1 for perfect similarity to -1 for perfect opposition.
And why that over something like just measuring the distance?
Because it measures the direction of the vectors, not just their magnitude. That makes it more robust to variations in document length. The faster the vector database can do this search, the lower your retrieval latency.
Okay, so the system instantly hands us, say, 5 short, relevant paragraphs from our internal docs. Now we move to phase 3, generation.
The final phase. This is where we marry the retrieved context with the LLM's linguistic power. It starts with prompt construction or augmentation. We don't just send the question to the LLM, we engineer a comprehensive prompt.
Right, the stuff, the context. What are the parts of that augmented prompt?
3 essential elements. First, the system message or prompt template. This sets the LLM's persona, its boundaries, its instructions. You are a helpful assistant answering only from the provided context. Second, the user's original query. And third, the retrieved top K data chunks. These chunks get injected into a defined context placeholder within that system message.
And because we were careful in phase 1 and 2, these chunks are targeted, they fit within the context window, and the LLM isn't overwhelmed.
And then the LLM executes the response generation. It processes this augmented prompt, leveraging its general knowledge for fluency and grammar, but critically grounding its specific answer entirely on the context we just provided.
Which minimizes hallucinations, enhances accuracy, and maintains relevance. The 3 big advantages of a RAG pipeline.
That's it.
That basic, naive AGI pipeline is powerful, but enterprise data.
Yeah.
It's complex, it's fragmented, sometimes it's even contradictory.
Right.
So what happens when developers realize that retrieval isn't perfect, that sometimes the LLM gets noisy, irrelevant chunks? This is where RAG evolves from naive to advanced and modular.
That's exactly right. The evolution of RAG is focused almost entirely on optimizing the quality of that retrieval. We're creating sophisticated filtering and rescoring mechanisms to make sure only the highest quality context makes it to the final prompt.
Okay, let's start with pre-retrieval optimization. These are techniques applied before the vector search even runs.
A crucial method here is metadata filtering. When we indexed our documents, we didn't just store the text and its vector. We also store metadata.
Timestamps, authors, document type.
Access roles, categories, exactly. So during a query, if the user asks for the 2024 policy update from legal, we can apply a filter that tells the vector database to search only within documents tagged with 2024, policy, and legal.
So it's a hybrid search. You're combining traditional structured search with semantic search.
And it yields far more precise results. And more importantly for the enterprise, that metadata layer is also how we enforce security.
Okay, that's fundamental. Explain that.
This is the linchpin of role-based access control, or RBAC, in RAG. We tag the document vector with metadata indicating which user groups can view it. When a user queries, the system first checks their role.
And then filters the vector search to only return chunks they're authorized to see.
Exactly. The LLM simply never sees documents the user isn't permitted to view.
A non-negotiable requirement for enterprise adoption. What about optimizing the chunking approach itself?
We refine it. We use fine-grained segmentation techniques like the sliding window approach. In naive RAG, chunks are often rigid. A sliding window creates chunks that deliberately overlap, but more importantly, it can dynamically adjust chunk sizes based on semantic breaks in the text.
So you're not cutting off a sentence or a key idea right in the middle.
You're preserving that context, which guarantees more complete and meaningful retrieval units.
Okay, let's move past the search. We've retrieved our top K chunks. Some might be perfect, others might be noise. How do we apply post-retrieval optimization before stuffing them into the prompt?
This is all about refining the relevance of that retrieved set. If we retrieve, say, 10 documents, we use re-ranking.
A second pass.
A second, more critical pass. We use a smaller, highly specialized language model, often called a cross-encoder, which is designed specifically for calculating sentence similarity, not generation.
Right.
This cross-encoder reads the user query and then scores each of the 10 retrieved chunks based on their actual relevancy to that specific query. It's a quality control filter.
So it pushes the most relevant 3 chunks to the top and just discards the rest.
Precisely. It significantly reduces the noise in the final prompt, increases the chances of an accurate answer, and often lowers your token usage because you're sending fewer but higher quality tokens.
That's clever. What if the total set of relevant chunks is still too long, even after re-ranking?
Then we use context summarization. If the retrieved chunks collectively are still too large, or if the main LLM is just expensive to run with massive prompts, we use a smaller, faster model, maybe an open source model optimized for summarization.
And that smaller model.
It reads all the retrieved chunks and generates a concise, focused summary. We then send that summary plus the original question to the main LLM.
But wait, doesn't introducing a second model for summarization add another potential point of failure? I mean, what if that summary model misinterprets the retrieved chunk?
That is a critical trade-off. You've hit on a major challenge of advanced RAG. Summarization is a double-edged sword.
How so?
While it saves tokens and speeds things up, it does introduce a risk of semantic drift or factual distortion if the summarization model is poorly engineered. Mitigation there requires really careful tuning and validation.
Okay, let's move to the cutting edge. Modular RAG. This is where the system stops being a linear pipeline and becomes more like an adaptable ecosystem.
Yes, modular RAG is the true realization of RAG's potential. It introduces enhanced adaptability by incorporating specialized, interchangeable components designed to handle complexity, multiple data sources, different query types, conversational memory.
Give me the most powerful example of a sophisticated search strategy here.
That would have to be RAG Fusion. This strategy is designed to overcome the problem of a user asking a single, maybe ambiguous, question that might miss key semantic terms.
Okay, walk me through it.
A user asks, how much did the company invest in cloud services last year? RAG Fusion intercepts that single query. Step 1, it uses an LLM to generate multiple, parallel, hypothetical queries that are semantically related but phrased differently.
So it might generate something like, what was the capital expenditure on AWS in 2023?
Or break down the Q4 IT spending for the prior fiscal year, or details on infrastructure investment. It proactively broadens the search scope before it even hits the database.
I see.
Step 2, it runs parallel vector searches for all of those expanded queries. This vastly increases the recall, the probability of finding all relevant documents. Step 3, the results from all searches are aggregated, intelligently re-ranked, and then used to augment the final prompt.
It's more computationally intensive, but the search results should be vastly more robust.
Significantly. And the other massive hurdle in conversational AI is remembering context across multiple turns. Modular ARGA addresses this with the memory module.
Which is transformative for building stateful conversational AI.
It is. Instead of a stateless single-turn query system, it creates an unbounded memory structure. When a user interacts with the system, not only is their current question vectorized, but the entire history of the previous turns is also vectorized, stored, and retrieved dynamically.
So if I ask about product X in the first turn, and then in the second turn I ask, what is its price?
The system retrieves the contextual document and the memory vector confirming you were just discussing product X.
That's the mechanism. It allows the system to understand follow-up questions, improving coherence and utility for long-running business conversations.
Yes. Okay, shifting focus now to the real-world deployment. ARGA is transforming how large organizations manage and access their internal knowledge. For the learner, this is probably the most important section, the operational reality.
What are the primary enterprise benefits driving this massive investment? It has to be more than just the answers are better.
The foundational benefit is cost efficiency and scalability. We hammer this point home because it's a financial imperative. Orgi drastically lowers the capital expenditure of constantly training and updating massive foundational models.
You maintain one robust LLM provider and just manage your data pipeline.
Right. And that model scales infinitely better as your data grows. And operationally, it becomes a phenomenal, unified knowledge management solution.
Because enterprise information is so siloed, SharePoint, Jira, Confluence.
Exactly. Ori creates a unified natural language interface to query all those diverse sources at once. It democratizes information access.
Which leads directly to personalization, the holy grail of customer and employee experience.
Precisely. Because the RAG system handles retrieval, it's the perfect point to incorporate private user history or specific organizational context like the user's department or past support tickets.
Enabling highly tailored, context-aware responses that no generic public LLM could ever replicate.
But, and this is a big but, anytime you introduce proprietary data, complex pipelines, and machine learning, you invite critical deployment challenges.
The pitfalls. What are the major ones we need to detail?
The first category is operational, accuracy, and data quality. Enterprise data is famously messy. It's inconsistent, it's stored in different formats, it's often outdated. If your data cleaning pipeline fails, RAG will deliver inaccurate or hallucinated outputs.
The garbage in, garbage out principle, which is deadly in a financial or legal context.
Absolutely. And even if the data is perfectly clean, the LLM can still struggle to find the right needle in the haystack.
That's the second challenge. Relevancy and context sensitivity. An ambiguous query can lead to irrelevant documents being retrieved.
Right, which leads to document relevance issues where the LLM has to synthesize an answer from a noisy, misleading input. This is why those advanced RAG techniques like re-ranking become so essential.
And the third, and for IT leadership, arguably the most crucial, is security and compliance. This is completely non-negotiable.
Absolutely. The stakes are immense. You're protecting trade secrets, financial data, PII. You must implement robust access controls. A user must never see an answer based on a document they don't have permission to view.
And that security has to extend to the storage itself.
Correct. Ironclad data security encryption at rest and in transit. And finally, audit trails are mandatory. To meet compliance like GDPR or high pay, every document access to generate a response has to be logged and auditable.
That level of traceability sounds complex to maintain in a dynamic system.
It is.
So we have major risks, data quality, relevance failures, security exposure. What are the practical mitigation strategies?
The technical mitigation has to start upstream. You combat data quality issues by investing heavily in specialized data cleaning and validation practices. You build dedicated data pipelines to standardize formats and flag inconsistencies before the indexer ever sees the document.
And for the compliance overhead?
That requires a comprehensive compliance management framework integrated directly into the RA architecture. This means continuous monitoring and ensuring those RBAC metadata filters are consistently applied and verified.
And what about that need for personalization without exposing sensitive user PII in the prompt?
There, we rely on security-preserving strategies like data anonymization. For example, in the memory module, you can replace sensitive identifiers with non-traceable tokens before using them to personalize the prompt. The goal is to maximize context while minimizing data exposure.
Okay, we've established the theoretical and enterprise necessity of RAing. Now let's pivot to the practical implementation. For Java developers, this used to mean messy, multi-language glue code.
Typically bridging Python libraries with the Java ecosystem, yeah.
But Spring AI changes the game by providing these native, clean abstractions. How do they map the naive RA process to their framework?
Spring AI's design philosophy is all about abstraction and convention over configuration. They introduce a really clear architectural separation, visualizing the naive RA process in two distinct layers.
Tell me about the top layer. How does that map to our phase one, indexing?
The top layer is the ETL, or offline process. This is the background job responsible for the indexing side of RAG. Within Spring AI, this layer handles data reading with a document reader, splitting with a text splitter, creating embeddings, and finally persisting everything into the configured vector store.
It's asynchronous. It's not part of the live user query.
Exactly. The bottom layer is the runtime phase. This handles the live user prompt, typically triggered by a controller endpoint. It initiates the similarity search against the vector store, performs the prompt augmentation, and then executes the LLM call using the chat client abstraction for generation.
And before we get into the code, what are the technical prerequisites? What does a developer need to get this running?
The complexity is really managed by Spring Boot conventions. You need a few core components, a relational database, commonly Postgres with the PG vector extension. You need access to the LLM and embedding services, so an OpenAI or Azure API key, and a modern Java environment and Spring CLI or Maven. The beauty is that Spring AI lets you swap out the vector store implementation without changing your core application logic.
Let's walk through the steps for unstructured data ingestion, using a PDF document as our example, like the CVS annual report from the source material.
Okay, the core ingestion logic would live in a Spring component. Let's call it the data loading service. This service orchestrates the entire ETL process defined in that top architectural layer.
So how does this service handle reading and splitting the PDF?
It relies on specialized interfaces from Spring AI. It would use the Page PDF document reader to read the PDF, converting pages into basic document objects. It then pipes that output into the critical step, applying the token text splitter.
And in the configuration, the developer would specify things like chunk size, 1000, and chunk overlap, 200.
Exactly. This ensures each segment is semantically rich but safely fits within the context window.
And once those clean overlap chunks are generated, how are they vectorized and stored?
The service then just calls the configured vectorstore.addDocuments method. This is the abstraction layer. Under the hood, the vector store implementation calls the configured embedding model, generates the numerical vectors, and then stores both the vector and the original text chunk in your Postgres database. Indexing complete.
That's the offline part. Now, for the runtime phase, the prompt structure is crucial here.
It is. The heart of the generation phase is the prompt template, often a file like system-stuff.st. This template defines the constraints and context for the LLM. It's where you set the persona.
Something like, you're a financial analyst assisting with questions about CVS's performance. Answer strictly using the context provided.
Exactly. And the absolutely non-negotiable element of that template is the context placeholder.
That's the ejection point.
That's where the retrieved .k chunks will be inserted milliseconds before the prompt is sent to the LLM.
And what service handles that whole runtime orchestration?
That would be handled by the application's QA service and exposed via a controller. The QA service receives the user's question, calls the vectorstore.similarity search query to perform the retrieval, then dynamically builds the final prompt.
It gets the document objects back, formats them, injects them into the context placeholder.
And then passes that completed augmented prompt string to the chat client to execute the generation call.
Okay, let's use the real-world example from our sources. A user hits the API with the question, who is the CEO of CVS? And that info is only in the index PDF. What confirms the IRReg implementation worked?
The confirmation is the highly specific answer, like, the CEO of CVS is Karen S. Lynch. This is so significant because it proves the system didn't use the LLM's general knowledge.
Right.
It successfully performed the vector search, retrieved the specific sentence from the proprietary PDF, augmented the prompt, and used it to generate a grounded, verifiable response, all using standard Spring conventions.
That PDF example covers unstructured text. But enterprises are equally full of structured data JSON, CSV files.
Product catalogs, employee records, inventory lists. Yep. And Spring AI's versatility is crucial here because it uses the same core RAG abstractions.
So if we want to ingest a bikes.json file with fields like name, price, description, what changes in the ETL process?
The core indexing retrieval generation phases stay the same, but the ETL structure has to change to account for those discrete fields. Handling structured data requires a more explicit, developer-defined method of ingesting the relevant fields.
So we're moving from a generic document reader to a dedicated structured reader.
Precisely. Instead of the Page PDF document reader, we'd use the specialized JSON reader class. And critically, the ingestion pipeline would introduce a custom component, like the product metadata generator class mentioned in the sources.
And what does that generator do?
It handles the transformation, it explicitly extracts the JSON fields, name, price, description, tags, and either formats them into descriptive text chunks or attaches them as index metadata before they're sent to the vector store.
So it's making sure that when the final chunk is created and embedded, it carries all the necessary product attributes, allowing the LLM to access the price or model name directly.
That's exactly right. It makes the data machine readable and semantically searchable. This allows the LLM later to generate answers that reference specific data points like price or warranty, not just a general summary.
So if we test this new pipeline against the bikes.json file,
We can query the system with a natural language question that requires structured recall, like, what is Hyperdrive Turbo X1? The system retrieves the relevant chunks from the JSON file, and the resulting answer is detailed and factual, grounded in that structured data.
and that confirmation really highlights the key takeaway for the learner.
It does. The final synthesis is that Spring AI provides the necessary unified abstractions, the vector store, the chat client, the prompt templating that let developers switch seamlessly between unstructured and structured data,
And swap out the underlying LLM or vector database providers.
all while maintaining the high-quality, grounded responses that RAG enables. It abstracts away the massive complexity of the underlying vector mechanics and network calls a Java developer would otherwise have to manage manually.
Wow, that was a truly comprehensive deep dive into RAG and Spring AI. We started by grounding the entire necessity of RAG in those foundational constraints of LLMs, the static knowledge cutoff and the limiting context window.
Establishing RAG as the only scalable path for enterprise AI.
Then we broke down the three critical stages of the naive RAG pipeline. Indexing, with its crucial decisions on token chunking and overlap, the vector-based retrieval process, and the final prompt augmentation and generation phase.
We spent significant time exploring the evolution, highlighting advanced techniques like pre-retrieval optimization through metadata filtering, which is how we implement security, and RBAC and post-retrieval strategies like re-ranking.
We then looked at the cutting edge of modular RAG, focusing on the powerful RAG fusion strategy for maximizing recall, and the foundational concept of the memory module for stateful conversation.
And we grounded all of it in the enterprise context, discussing the benefits like cost efficiency, but also the non-negotiable challenges of data quality, relevance failures, and the stringent demands of security and compliance.
And finally, we saw exactly how Spring AI makes this real for the Java world, defining that clear architectural separation between ETL and runtime phases, and walking through practical implementations for both PDF and JSON data. It's clear RAG isn't optional, it's essential.
As a final provocative thought for the learner, we detailed how modular RAG's memory module works to create an unbounded history by vectorizing and retrieving past interactions.
Okay.
Today, many enterprises use RAG for simple Q&A. They treat it as a transactional search layer. But when RAG fully integrates that memory module, allowing for genuinely unbounded stateful memory retrieval, not just of documents, but of the entire conversation, history RAG ceases to be just an architectural pattern.
It becomes what?
It starts becoming a fundamental requirement for building AI agents.
Meaning the system could merge real-time RAG context retrieval with the entire history of a user's conversation into one seamless, constantly evolving experience. It could execute complex, multi-step business processes over days or weeks.
Exactly. It sets the stage for AI agents that don't just answer questions about the past, but actively participate in, track, and manage long-term context-rich business processes. That seamless merging of external context and internal conversational state, that is the next frontier of enterprise AI.
A truly integrated, intelligent partner. Thank you for guiding us through this incredibly deep dive. That's all the time we have. Now go forth and apply this knowledge. We'll see you next time.